In this orthokeratology case, we've got a baseline topography where doing editing of the map, the software introduced this artifact, this ring, into the data, and that is translating into a ring on the lens, on the curvature on the back of the lens, where it's very, very steep here in the alignment zone, and that's affecting how this lens fits on the eye. Without another map to design from, one option is to create a simulation, and the way to do that is to go into the Wave software, not the Scout software, but the Wave software, and just open that, and it'll give you a blank new lens. I'll do that right now. So it just gives you this window with no data in it. You go to the File button and you create a new simulation. And then what you can do is just plug in your numbers from your patient. So let's move the windows around so we can see what those are. So it's at axis 27. E value in the steep meridian is 0.4. The other SimK was 4258. And the E value here was 0.37. We will not average. And then from here, what we can do is just duplicate the other parameters in the patient's lens. So we'll use the same refraction. We have dimensions of 6.0, 6.6 with a 10.9 diameter. So create a new ortho K lens. And now we have a new lens that is similar in parameter, most parameters, to the existing lens, but it's based off of a simulated topography. If we compare it to patient's actual lens, topographies don't look very similar to one another, but some of this is artifact, and without other data to go off of, this is an option. So from here, we can choose to maybe just save and then order this lens. You can save this lens with the patient's data. The other thing that is possible is to go and look at the back surface, and we can see that here in the alignment zone, this alignment curve gets up to about 35 diopters or so. In the existing lens, we can see it's a much steeper curve. This one gets up to 46, 47, about 47.5 diopters. So we have about a 12 diopter difference between the two curves. And one thing we can do is, on the existing lens, just lift the last dot, and you'll see this curve start to drop. So we're now around 40. .34, maybe we're a little too flat. And so now we have a back surface curvature that looks a little bit more even, still maybe a little bit steep here in this quadrant. It can be touched up if needed. But this is another option. If you look at the simulated tear graph, it's going to look pretty wild with crazy amount of clearance out here. But yeah, this is based off a topography that's not really true to life. So this is going to look quite odd. This case will probably depend a little bit more on how the fluorescein looks, because we're not going to be able to rely on the simulated data here. But these are two ways to create a lens that should fit a little bit better. We're kind of guessing where the patient's cornea really is, but without other data, this might be the best avenue. So hopefully this is helpful. Best of luck with your patient.